Right. So this morning, we have a couple gentlemen from Calcul, Quebec. The first is Frederick Lefebvre. He's an HPC systems engineer, team lead at see, I almost did German. I'm going to screw it up anyway, so I'll just say the University of Laval Advanced Computing Center. He's a member of Compute Canada's National Storage Team and sometimes presents himself from Calcul, Quebec. Also, we have Simon Guilbault. He is an HPC engineer at the University of Laval. I'm checking the next page to make sure that I've got it all. Okay, groovy. Please, let's give it up for Frederick and Simon.
Woo! Thank you, Steve. So today we'll be reporting on our experience in developing HSM Copytool for object storage and Lustre. We will give an overview of the rationale of why we initiated that project, go into some details on the way that we did the implementation and some hurdle that we had to overcome, and then show some benchmark because everybody likes to see charts in those presentations. And we'll finish by covering the limitations of our Copytool and discuss some of the issues that we noticed in Lustre's implementation of HSM while doing that project. So I need to excuse myself for those slides first. It's the first time that I see the PowerPoint version of them, and I should not have trusted the translation from our tool that we use. So we are from the Advanced Computing Center at the University of Laval. We're part of Compute Canada and Calcul, Québec. We've been running Lustre since 2009, and currently we manage about 2.5 petabytes of Lustre storage serving 2 parallel clusters. So why did we start this project? Most people that I've discussed it with have said either like, wow, that's cool, or why the hell? So my users are just like yours. They want to have more storage. They will rather not have to pay for it or have it for very cheap. And of course, they want to be able to run their parallel workloads from it, and they don't want us to hassle them about moving their data somewhere else. So this kind of calls for a single namespace kind of environment. And just to push us over the cliff and starting the project, we've had bioinformatics users coming to us lately with kind of creative solutions, way too creative for our liking, from non-traditional vendors to try to address those issues that I've just described. So we figured we needed to be in front of the wave and find something for them before we end up managing their systems. And timing it was right for us here because Compute Canada, our national organization that pretty similar to Exceed here in the US, is in an acquisition process for a couple of tens of petabytes of object storage to be deployed centrally and made available to our users and all of our existing computing sites. So we kind of like the idea of being able to tell our users, well, yes, you want 2, 3 extra petabytes and you want them for cheap. Well, let's use this existing resource at Compute Canada and extend our parallel storage that we have available attached to the computing resources. So it kind of answers the need to be able to submit parallel jobs from the Lustre file system and offload the long-term storage of the data transparently to this central object storage. So while starting the project, we had to consider which API, which object API we should be using for the communications. We initially considered Ceph because it's what we've been using locally at University of Laval. Then we have to take into account that Compute Canada object storage is not chosen yet. It was not 6 months ago when we started the project, and it's still not chosen, but it should be announced in the next couple of weeks, hopefully. So Rados, the native API for Ceph, which looked like an obvious choice for us, might be too restrictive in being tied to Ceph only. We considered using the existing POSIX Copytool by using the POSIX gateways to those object storage, but the scalability and stability of that solution, especially when considering long-distance networks across the country, wasn't clear to us. So we limited Ceph, Rados off the bat as being limited to a single vendor, even to its open source. And we only considered the two generic APIs, which is S3, which is well supported by most object stores, and Swift. Swift looked really appealing to us in the beginning because it looked much easier to implement. But the C library for Swift has been unmaintained for 2 years, so it's kind of scared us away. And we already knew that the Swift implementation in Ceph's Rados gateway differs from other implementation we've seen. So it was kind of a worry here also. And it doesn't help that the authentication for Swift is much more complicated than S3. So we started that project by reusing the POSIX Copytool that was contributed by the CA folks in the Lustre source tree. And we modified it to do S3 puts and gets. Initial version was really simple. And because we hit some issues initially when we tried to scale it, we also implemented a Rados version, which I just said that we will not do, just for validation to try to identify if the problem was with our underlying storage system or if it was in our implementation. In doing so, we noticed that there was about 30% of the code in all three Copytools that I just mentioned, the POSIX Copytools and the two object Copytools that we developed were common. So we modularized it in an external library that could be reused by future implementators of Copytools for Lustre. We put it in a libct library that is also included with our source code. libs3 merits its own couple of slides. It's been fairly easy to work with. It's an easy implementation. Some issues we had with it. First, it's not really available on CentOS systems. We need to use extended repositories to install it from RPMs. The numbering of the libs3 releases hasn't changed in 5 years. All through the code has changed a lot. So take a RPM from 2 years ago and your RPM from this year, and you're going to have the same version reported by both, while it's a completely different set of code. And the changelog has not been updated in 8 years. So it's still maintained, but it's kind of loosely packaged. In our initial test also with libs3, our Copytool segfault held under stress. Copying multiple large files will usually end up with a segfault, either in libs3 or in libcurl, the HTTP library. So to work around those issues, first we started using the latest source repository from libs3 to make sure that we knew which version we're actually using. And we needed to patch libs3. It's a very simple, 2-line patch that is also provided with our source code to go around the segfault that was happening in libcurl. So the patch and instruction is provided. And maybe I should have moved that to the end of the presentation, but maybe a shortcoming of implementation is that we only have tested it against Ceph's Rados gateway, and we haven't. Which is Ceph's S3 implementation, and we haven't used it with Amazon's S3 implementation, but we assume it will work since we use a common library. So for people that are not familiar with HSM on Lustre, just a quick recap of how it actually works. Basically, everything is managed centrally by the MDS servers, which receive commands from Lustre clients or the policy engine of Robinhood. Either way is fine to initiate an HSM action like archival or restoring a file. And then you have the Copytools who just register with the coordinator on the MDS server and will receive HSM action items to act upon. And past that point, the Copytool is just a basic data mover moving data between two storage systems. In our case, part of it is done over POSIX for Lustre, and the other part is done over S3 to interact with the object storage. So we've been using Ceph for our development and internal testing. The S3 is implemented in Ceph in the Rados gateway. It's the gray box we see on the left there, which uses the librados, which is the native object API for Ceph to interact with the underlying storage. So basically, the Rados version of the code, just goes straight to the librados, and in fact, the code is much simpler. So same thing here. So the Rados gateway receives the S3 calls to HTTP, and just interacts there with the object storage daemon and the monitors and Ceph to push and get the data from the underlying storage. And Simon will go into the details of the implementation. Sorry.
So we use the Lustre file ID to store the object to identify each object on the S3 bucket. So in the path, we have the bucket prefix that is only there to have multiple HSM Lustre storage storing their HSM object on the same gigantic storage. So we can have like you have all HSM archive and somebody else in the same backend without any conflict. The bucket ID is only there to shard the request in multiple containers, because S3 is not really good with a million of objects in the same container. So that is a simple way to spread out that load. And we are storing objects in multiple chunks because S3 is limited in the size of these requests. So we are storing them in 100 megabyte chunks. And we are not using a multi-part upload because there is a 5 terabyte limit, and it's more complicated to handle these kind of requests. And we are also using compression with LZ4, like ZFS is using. So this also reduces the problem caused by sparse file, because the bunch of zero, the sparse file will be compressed well. So we'll not store a bunch of zero on the S3 storage and just fill it up with the useless data. S3 also do the checksum of each object. So we also check when we download back those objects and restore those files, we check if the MD5 sum match what we are restoring. So the bucket sharding is only there for accelerating the storage. It's only to handle a problem with the S3. So we put some metadata on each object to be able to restore properly. So we store the compression algorithm we use, so we can change later on to, instead of LZ4, we can support anything else. And we store the MD5 checksum. And the size of each chunk and the total size of the file is only there to allocate the proper buffer when restoring those files. We also store the UID and GID and a few other parameters in the object store because, well, that storage is cheap, so maybe it could be useful in a disaster recovery. But that data is already in Robinhood, so it's a better idea to back up the Robinhood MySQL database instead of using what we store on the S3 object. So to make these tests, we use hardware from HPE. So last year, we had Gen 8 SL4540 that was used for Lustre, but this time we use it for Ceph, and we're running the Hammer release on it. And we also had a few SSD in them for the journals of Ceph. We also have 2 Apollo 4520 that we use for Lustre. So that's the same thing that was shown yesterday by the folks from HPE. So these are all the servers that we use. And because Ceph need 3 monitor nodes, so we had a 3 server that was running the monitor. And, well, we need an MDS server, so we run that on one of these nodes. So it's not good for production, but it's fine for the test we have done. So Ceph support eraser encoding. So we tried that, and also replication. So with replication, well, we tested with 3 copies, so it gets expensive. So that's why the erosion coding is a lot better, and it's slower, but it's archival, so it's not really a problem. And we use 8+2 of erosion coding. So with 4 servers, we're not redundant, but for testing, it's fine because it's something for a benchmark. And the SSD that was used in the Ceph server, well, we only use like 40 gigabytes on them. So the other leftover, like 300 gigabytes, can be used to run VMs or anything else. And on the Lustre server, we use ZFS with the LZ4 compression. And also we had our large block in there. So we did a presentation last year. So on the server, we can get about 8 gigabytes of write and get 4 gigabytes of reads. So, but that's on the Gen 8 generation. Gen 9 should be slightly better. So our data set, because it was a genomic data that we're targeting for, so we use some files, just basically a big, gigantic ASCII file that compress well. With LZ4, go about to 1/3 of the size. And we also have the incompressible data. The BAM file is basically the same file, but compressed, so the genomic file use that. And to test, because genomic generate a lot of small files sometimes, we take the kernel source that have about 50,000 files, so it's just a stress test of IOPS. So the compression is a bit cheating because the data compress very well. So as you can see, the replication is a lot faster than erosion coding, and the Rados implementation is faster than S3. So that's expected because Rados have lower overhead than S3. So, and well, we also tested CFFS with the POSIX Copytool, and CFFS works, but the metadata server in there is slower. So that's why we're only getting about 13 files per second and 180 files about for the other implementation. So we're saying it's about the same thing. Rados is faster. And as you can see, Rados erosion is really fast, and mostly because the compression gives about 3 times improvement because it takes about 1/3 of the space. So Frederick will finish.
So the biggest limitation that we noticed, or the biggest issue that we noticed while running those tests, is that in every of our tests, the HSM restore was 30 to 50% slower than the HSM archive of the same files. In our specific case, in our test environment, our Lustre client will hang at regular interval while restoring files. And we will get soft lookup and CPU stuck messages filling the logs. And this is valid for all 3 of the Copytools that we have mentioned in that talk. So it's valid for the existing POSIX Copytool, our S3 Copytool, and our validation Rados Copytool that we've also written. Initially we thought something must be wrong with our test setup, and so we tried to tune our ZFS environment and went back over our notes from the installation and tried to figure out what was wrong. And so then we got our colleagues at HPE to also try our S3 Copytool to try to reproduce our results. And with their own independent setup, they came to the same conclusions. Also looking at some slides from DDN at LAD last fall when I don't remember the name of the presenter that presented about the WAS Copytool for Lustre. The benchmarks in their slides seem to point to a similar behavior. So it kind of gets me wondering, is maybe someone will be able to tell me later, it's normal, it's to be expected, or maybe something is wrong in our setup, or something is maybe an issue in Lustre's HSM implementation. But I will much rather have a faster restore than a faster archive, right? Because we may have jobs waiting to start on data being staged back on the Lustre file system. So it might be something worth digging into. And of course, we didn't try to implement partial archive or restore archive as they are not supported by Lustre yet. we did not implement the cancel operation for our HSM or Copytool. So if a file is being restored or is being archived or is being deleted, there's no way to cancel the operation midway. And we didn't address priority. And as I mentioned in the previous slide, I would have liked to implement in the Copytool some prioritizations of the HSM action items so to be able to prioritize restore requests at the detriment of archive requests. We can just wait for the resources to become available. And some weird bugs that we found in Lustre's HSM. A number of times when probing the MDS server for the number of ongoing requests, we got return a negative number of current requests, which doesn't hurt anyone, but it looks kind of weird in the logs. And a bigger issue, and our colleagues from CEA have confirmed to us earlier this week, they have seen the same thing on their side, that when changing the HSM Max Requests, while HSM is being activated, we quickly figure out it's a pretty bad idea. It works well when you try to increase the number of HSM Max Requests, but as soon as you start to decrease the number of HSM Max Requests, well, anything can happen. And what we've seen happening is, we go from, the example here, we go from 40 max requests to 20 max requests. And all of a sudden we see, 60, 200 requests, going on the wire. So the MDS servers kind of seem to lose the map here. And future work that we would like to address with this project, we thought about data indexing. So since when we're archiving data archiving files to S3, we already have to parse the whole content of the file. So we thought maybe we should try to characterize the file and index it in an external database or a non-relational database to try and make available that data directly to the users from the S3 objects, instead of forcing him to always go through the Lustre file system to access his file if he doesn't need the performance. And would like to see local mirrors on Lustre of S3 public dataset, and it's something that we haven't addressed. And I think it's an idea we stole from a set of slides from Intel last year. So just to finish, we'd like to thank our friend at HPE who have supported us by loaning us the hardware for the project, and would like to thank the folks at CEA for having committed back to the community most of what they have developed around Lustre, and this has enabled us to build on their previous work to develop that project faster. And to be nice to everyone to give back, our Copytool is available on GitHub right now, and if you want to use it and report back on your experience, we would like to have your feedback. Thank you.
Boldly springing into action. Thanks, Tim. So, questions?
Yeah, nice work. Actually, not a question, but I would point out that I don't know how Rados Gateway works with how it stores S3 keys, but in Amazon, and they've documented this in a performance tuning document for S3, the keys should be stored in, Amazon's sharding based on lexicographic order of the keys, so you want to have as much change happening with the keys as you store them. So their recommendation is if you're using a counter to reverse the digits, so the first byte is changing the most frequently, then you should get much better performance in a single bucket, because it will be sharding across multiple backends.
Okay, awesome feedback, thanks.
Did you submit bugs or anything for the problems that you've seen, or?
Not yet.
Okay, because they can't get fixed
well,
if nobody knows about them.
Obviously, we've been rushing to finish some work, and we haven't had time to properly document the issues. Confirmation from other people that I've seen other issues is a good motivation to submit something. Yeah.
So how come you guys are not using multi-part, are you doing, so, well, you said that you're the 5 terabyte limit, but does that mean you're doing chunking yourselves in your Copytool
Yeah.
and keeping track of all the parts that way?
Yeah.
But you're not parallelizing it, you're doing it sequentially?
Yes.
Yeah. So you could just multi-thread it and then that would take care of that problem?
Yeah, there's one thread per file, so.
It's kind of a side effect of having started from the POSIX Copytool, right, and sharing a common background. So it's parallelized at the file level, and we haven't addressed parallelization of a single file in the transfer.
And are you storing all the metadata associated with the file as well? You like tarballing it, kind of adding the owner mode, all that stuff, change time, access times, all that stuff?
Well,
Yes.
we're only storing in the S3 metadata that Simon mentioned earlier.
Yeah, it's a built-in method of S3, so it's a standard metadata on S3. You can add to your own field.
That's as you create the S3 object, it gets that information. But I'm saying, are you actually taking the file stat information and including it?
Yes.
Okay, as part of your object. Yeah.
Well, thank you.
Thank you both.